Hey, y'all, let's cover section 5.2. So talking about power function, a power function is a function that can be represented in the form of f of x is equal to kx to the p. K is always the coefficient and p is the power. So therefore it's a power function. All toolkit functions are power functions, and I can prove it to you. So if we have f of x is equal to 1, which is our constant, these are all of our toolkit functions, then I can also write this as f of x is equal to x to the 0. So, and then k would be 1. 1, anything to the 0 power is 1. So that is 1 times 1, which is 1. All right. Identity function, f of x, is equal to 1 x to the 1. Coefficient, power, and that's also equal to our x. X squared, f of x, is equal to 1 x squared. We've got coefficient and a power. Same thing. Cubic, f of x, is equal to 1 x cubed, coefficient and power. Reciprocal, f of x, is equal to 1 x to the negative 1. Remember the negatives, move it back to the denominator, which equal to 1 over x. Reciprocal squared, same thing, f of x is equal to 1 x to the negative 2, which is 1 over x squared. Square root function, f of x, is equal to 1 x to the 1/2 power over root. So that's a square root, so it'd have to be a square, which is equal to the square root of x. And then the last one is f of x is equal to 1 x to the 1/3, which is the cube root of x. Okay. Those are just proving that all of our power function, all of our toolkit functions are truly power functions. In behavior of whole number power functions. So in behavior is, on all of our graphs, they have cute little arrows that are pointing in the direction that the arrow is, the graph is going after we can't see it. Like this one is continuing on. It doesn't have the arrows, but let's create our arrows. The in behavior is what are these arrows doing? And you're going to write this a specific way. So the way you're going to write this is as x approaches positive infinity, f of x is approaching what? And then as x approaches negative infinity, f of x approaches what? So, and these are just arrows. These are just arrows. As x approaches positive infinity, well, starting from here, x is approaching positive infinity this way. So which direction is our arrow going? It's going up. So it's either going to be going up towards positive infinity, or it would be going down towards negative infinity. So f of x is approaching positive infinity. It has to do with up or down. Okay. Up is positive, down is negative. As x approaches negative infinity, so as it's going this direction, as our x's are getting smaller, our f of x, our y, is getting bigger. So it is positive infinity as well. This is going to be how you represent in behavior whenever I ask you to do so. Let's look at our cube function. As I'm going to rewrite it just the same. As x approaches positive infinity, where is the y values? Where are they heading? And then as x approaches negative infinity, what is happening with our f of x? All right, as we're going towards positive, we are going up, our arrows are going up, so therefore it's approaching positive infinity. As our x's are getting smaller, our function is going down, so therefore it is approaching negative infinity. And there is our in behavior for our cubic function. Really easy to do with a graph because you've already got it. Okay. There's a really neat thing that I'm going to give you this little tool right here. Those are just square and cubic functions. What about f of x is x to the 4th, x to the 5th, x to the 48th, x to the 77th? How do we know what our in behavior is for each of those functions? And I'm going to give you a little tool here to know what to do. Okay. if your coefficient is positive. So if your coefficient is positive and you have an even power, your n is even, all right, n is even, then it's going to look like this in some format. Could be, all right. When this happens, you're going to go as your end behavior is going to be as x approaches positive infinity, f of x approaches positive infinity. And this is true for any coefficient positive with an even power. This end behavior is going to be true. As x approaches negative infinity, f of x approaches positive infinity. It's going to look just like that in some, but prettier. All right, what if our coefficient is positive? So coefficient is positive, but we have an odd power, 3, 5, 7. That's going to look like what? Something like this, okay? And as x approaches positive infinity, f of x approaches, I can draw an arrow here, positive infinity. And as x approaches negative infinity, f of x too approaches negative infinity. And this is consistent across the board. What if our coefficient is negative? So a negative coefficient, but an even power. It's going to look like that. As x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity as well. Okay, that's the end behavior. What if we have a negative coefficient and an odd power? That's going to look more like this. As x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches positive infinity. Okay, we can use these to help us solve these problems. What if we want to describe the end behavior of f of x is equal to negative 3x to the 6th? I want you to pause the video and attempt to do this one yourself. Which one of these does it fall into? And then write what the end behavior would be. Okay, you just have to decide which one of these it is and then write it. Negative 3x to the 6th. All right, pause and then come back. All right, so we have a negative coefficient. And our n, our power, is even. And a power is even. So I just need to come up here and find a negative coefficient. Okay, these are both negative, but I need an even power. And so it's this one here. We can see just by looking at it as well. But because they gave us this, just using this is how I'm doing it. If I wanted to just look at it, I can see that as x approaches positive infinity, f of x is negative. And as x approaches negative infinity, f of x is negative. But verifying it with the function itself is fabulous. You need to be able to do that. So as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x too approaches negative infinity. And there's the end behavior. And that is describing the end behavior. That's my expectation of what you need to write. All right, there's a lot of words here, and I want you to pause the video and read through this because I'm not going to read everything to you, but you need to understand all of it. Okay, so pause and then come back and I'll be talking about it. This is the polynomial function. All right, and you could have so many different opportunities here for what it could look like. And polynomial function usually just means that there's going to be a bunch of twists and turns, or there might only be one twist and turn. But the thing you need to understand is the first thing you need to do when you get a function and when there's numbers and everything, and it's truly a polynomial function, you need to put it in order from your highest exponent to your lowest exponent. It needs to be in order, okay? Specifically because you need to know what the leading term is. And the leading term is the one with the highest degree or the highest exponent. Highest exponent is the reference, okay? That is your leading term for your polynomial. You need to know your leading term for your polynomial in order to know the end behavior as well as other things that we're about to describe. The degree of the polynomial is the degree of the leading term, okay? The leading coefficient is the coefficient of your leading term. The leading coefficient is the coefficient of the leading term. So I want to give you an example. Let's go back to that other one. It was negative 3x to the 6th. So say we have f of x is equal to negative 3x to the 6th plus 5x to the 5th minus 4x. All right, let's just say we have that. Our leading term is negative 3x to the 6th. The entire thing is our leading term. The degree of this entire polynomial, the degree, which is also called n, is equal to 6. It's the exponent. All right. The leading coefficient is just the negative 3. Not the x, not the x to the 6th. It's just the negative 3. Okay. Characteristics of polynomial function. The max number of zeros, which are your x-intercepts, is the same as the degree. So for the one that we're referencing up here, the most number of zeros we can have are 6. All right, that's the most number. I'll give you another example here. If you have x to the 4th as the leading term, the max zeros is 4. The maximum number of terms, however, is n minus 1. So using the one that we're using here, it's 6 minus 1. So the max terms is 5. Polynomials have ends that head to either positive infinity or negative infinity. So, but in between there, it can have lots of terms. It can have all sorts of crazy fun stuff. But the max terms is always going to be the degree minus 1, all right? Or the highest exponent minus 1. I'm going to be using the word degree moving forward. If you have x to the 4th as a leading term, then the maximum number of terms you can have is 4 minus 1, which is 3 terms. Polynomial graph consists of terms and end behavior that goes to positive or negative infinity solely based on the leading term. And we just discussed that in the negative 3x to the 6th. Okay. So this is something similar to what you're going to see on your exam. I'm going to give you a polynomial function. It may or may not be in order. You need to make sure that you understand that the highest degree, the highest exponent, is going to be your leading term. All right. Now, first thing I ask you is, what is the degree of this term? I'm not asking you of the polynomial, of this term. The degree of the term 3x to the 4th is 4. What is the coefficient of negative 7x? I did not ask for the leading coefficient of the polynomial. I'm asking what's the coefficient. You need to understand what a coefficient is. It's the number in front of the variable. So it is negative 7. Now, everything else is going to reference everything else we've been discussing up to this point about the polynomial itself, not specific terms. What is the leading term for this polynomial? And the answer for that is 3x to the 5th. That is our highest exponent. It's our highest degree. So therefore, it is our leading term. It includes the coefficient, a sign if there is one, and then the power with the variable. What is the degree of f of x? The degree is the highest exponent, which you can find by using your leading term, and that is 5. What is the leading coefficient of f of x? Again, you're going to use your leading term to find this answer, and it is 3. Everything that we decide from here down is strictly based on the leading term. I don't even need to look at the polynomial function. What are the max terms for this function? Well, max terms is n minus 1, Remember, n is the degree minus 1, and our degree is 5. So 5 minus 1 is 4 terms. That's the max number of terms this polynomial can have. What are the max zeros for the polynomial? The max zeros, remember, is your x-intercept is equal to your degree. So your max zeros is 5. What are the end behaviors of the function? Well, we need to just look at the leading term. Yet again, it's positive and it has an odd power. So positive with an odd power, we need to look back. And so that should let you know that if you don't have this part memorized, you're going to want to have this access to this information on your exam. Just a heads up. Okay. So we have a positive coefficient. We have an odd power. Positive coefficient, odd power. This is what our function is, our polynomial is going to look like. Something like this. It might have some terms in here. So max terms is 4. So it actually would look more like 3, 1, 2, 3, and then it's got to go back upstairs somewhere. All right. So that's going to be as x approaches positive infinity, what's f of x doing? As x approaches negative infinity, what's f of x doing? As it's approaching positive infinity, f of x is approaching positive infinity. As x approaches negative infinity, f of x is approaching the negative infinity. And this is the end behavior that I'm expecting. Given the polynomial, g of x is equal to negative 2x, x minus 4 squared times x squared plus 1. Be very careful on this, all right? I do not need you to multiply this whole stinking thing out. All I need you to do is focus on the x's. So when I see this, the first thing I say is, okay, I take the x's and everything that's attached to the x. So negative 2x I need. This is just x, and it's going to be squared times x squared. It's the highest number I'm going to get out of that. And then I've got another x squared. All right, multiplying these together. That's negative 2x to the 5th. I want to do this one, and I want to do one more that I'm going to give you just because I had all but one person miss it on my exam last time. I want to make sure you understand what's happening here. The leading term of g of x is negative 2x to the 5th. That's the leading term. The leading coefficient is negative 2. The degree is 5. The max number of terms is 5 minus 1, which is 4. What else could I possibly want to know? The max zeros is 5. And then now the end behavior. This is a negative coefficient with an odd power, which is going to look like this. But actually, it's going to have the squigglies in between. Okay. So let's talk about the squigglies. How many squigglies could I potentially have here? I could have 4 terms. So 5 minus 1, I could have 4 terms. Could I have 3 terms? I couldn't, because then my end behavior would be wrong. So the next amount of terms I could have is 2, because it's going to have to start up here and end down here. In order for me to make that happen, I can have 2 terms, or start up here and down here. I could have 1, 2, 3, 1, 2, 3, 4. 4 terms. I have to have one of those 2. Okay. I could not have 0, 1, 3, or 5 terms. It's going to be either 2 or 4. So our end behavior, as x approaches positive infinity, f of x is approaching negative infinity. As x approaches negative infinity, f of x approaches positive infinity. Let's look at these 2 graphs. Oh, I wanted to go back and do that other one real quick. Say instead I had, instead of just this one, let's say I have negative 2x And then I have, let's go with 3x minus 4 squared, and then x squared plus 1. The part that people missed here is they did not keep 3x together. So your leading term would be negative 2x, 3x squared, and then x squared. It's the highest value you could possibly have, which is negative 6. Nope, it's not. This is 3 squared. So that's negative 2x, 9x squared, and x squared, which would be negative 18x to the 5th. That's the leading coefficient, or the leading term. Okay, be careful with that. You've got to take the number that's attached to the x as well when you're squaring it. Don't just take the x's. All right, let's go back to this one. Given the graph of polynomial, what's the number of turns? 1, 2, 3. Number of zeros is 1, 2, 3. And the degree is at least, ooh, we're going backwards here. If we know that n minus 1, which is degree minus 1, is equal to our turns, then I can solve for my degree because I know how many turns there are. So n minus 1 is equal to 3. Solving for n, I just need to add 1 to both sides, and n is equal to 4. That is my degree, is at least 4. Okay. Look at the next one. Number of turns, 1, 2. Number of zeros, 1, 2, 3. Remember, that's your x-intercepts. The degree is at least what? Well, again, n minus 1 is equal to my turns. My turns is 2. Solving for n, my degree is at least 3. Okay. The degree should be at least the number of zeros. So we've got 3, we've got 4, so we're good. We're good on both of those. You just need to make sure to be very careful that, let's just say that you may have, fewer turns than we do zeros. That, I don't know how that would happen necessarily, but you need to make sure that your n is at least what your zeros are. Okay, it can be more, it just can't be less. And that's it for 5-2. Let me know what questions y'all have.